So as soon as you see these structures, what's your first thought? These structures that you see. What is that, right? Your first initial thought is, I'm not doing this. And you skip it and you move on. Don't freak, okay? Just stare at it and hopefully something will jump off on you, all right? So the structure for glucose. Well, the first thing you know what glucose is, right? What is glucose? It's sugar. Yeah, I mean, that is your basic sugar that's in all of biology that you studied. All right, and cyclohexane, that's more of something that you don't recognize, okay? Staring at the structure itself, what do you notice in terms of similarities and differences? Let's go with similarities first. They're hexagons. That's the first thing I want you to notice. Cyclo, what do you think cyclo means? It's like a circle, and hex means what? 6. So it's a hexagonal shape. Okay? So you have C6H12O6 and C6H12. That's a similar feature. Okay? But what about some of the features that are not the same? Okay? Let me tell you this. This hexane looking structure, ooh, that's not good. It's called a benzene ring. Okay? That's a horrible. Let's do that. Maybe that's a little better. And at every point of the hexagon should be a carbon. And again, this is all organic nomenclature, but at every point there should be a carbon. However, in glucose, do you see that? What's kind of funky about the glucose? Very good. One of these has an oxygen. All right. What else do you notice the difference between glucose and cyclohexane? Very good. We have OH here, OH here, OH here, and then all the way out here, our C shows up with another OH. Oh, right there. Sorry. Basically, it's the oxygen attached. Now, what about cyclohexane? Well, remember this thing's three-dimensional. So this H and this H are kind of standing up, pointing out of the board, and this H and this H is also standing up, kind of pointing up. So it's a three-dimensional. Yeah, the other two are down below it, kind of deal. But what do you notice about this thing? It's pretty much nothing but what? C's and H's. So it's pretty balanced, right? So in terms of polarity, what do you think this thing would be? Very good. It's nonpolar. Okay. Now what do you think about this other thing? It's definitely polar. With all those oxygens involved, this molecule is most definitely polar. Okay. So question 1. Identify the types of intermolecular attractive forces that you would have here. Let's talk about pure glucose first. Okay? Well, we've already established that it's what? Polar. So what types of IMFs do polar molecules have? Hydrogen bonding and dipole-dipole. It's that simple. Hydrogen bonding. Now, the way they have it listed.
Mr. Richards?
Yes, ma'am.
Hey, this is Michelle and Stewart. Are you available to come down for a Q&A conference?
Hang on just 1 second, okay?
Okay.
I'm recording a lecture and it will not pause.
Oh, I'm so sorry.
No, you're fine. Just 1 more second. It's not working with me. Come on. Seriously? Yeah, I'll just cover it up. Hey. I am actually in the middle of an AP chemistry review session right now.
Did you get my email last week about the conference?
I did, and honestly, I completely forgot about it because our AP exam is next Monday. Do I need to come down there?
Well, I don't know if you could for a few minutes. They're both here, and
Am I the only teacher still in the building?
Yeah, you have that pollen hub and the fold.
Okay. All right.
No, see,
Let's start this back up. So we have pure glucose, which we've already said has what in it? Hydrogen bonding, or, and again, I think I stopped right there. So I'm just going to go ahead and rewrite H bond, or, and again, the key word there, the way they have it written, is or dipole. Now, you've got to remember something, and this is something that I haven't done a great job of explaining, but it's something that is a fact. The way that it works is LDF is the weakest. Dipole is the next strongest, and then H bond is the strongest. The way that this works is if it has a hydrogen bond, it also has a dipole and an LDF. Does that make sense? If it's a dipole, it also has an LDF. But if it's a building concept.
the lady at the
Uh-huh.
section talked about that, and that confused me because I didn't know if you had.
It's not one. It's an order. It's a growing order. So if you have the strongest, you also have everything below it. But if you just have an LDF, that's it. That's all you can have. And that's only between two non-polar molecules. Okay. Now, since we have labeled this cyclohexane as non-polar, what is the only kind of LDF that it can have? So IMF. The only one that it can have is an LDF. Now, they actually call it a van der Waals force interaction. Did y'all see that? Again, it wasn't recording whenever y'all looked at this. But if you go back and you look at the key right here, again, this is old terminology. You will never use this again. Van der Waals is the old school term for London dispersion. Okay, so technically, you could say that pure glucose has hydrogen bonding, or it has dipole, or it has an LDF. So 1 point is earned for what? A correct answer. You could say any one of them. So how dumb is that? Really, they say, what is an intermolecular force? If you list any of the three, you get a point. That is super nice. I personally think that the only answer you should get credit for is hydrogen bonding. Me personally. But again, now this one is specific. Pure cyclohexane only has an LDF. Why? It's only non-polar. Now, I'm going to be honest with you. More than likely, this will not be a style of question they're going to ask. It will be, what type of IMF? And guess what? Why? You'd have to explain it. But because it's polar and because it's non-polar is essentially how you could explain it. All right. So now looking at the other picture. All right. Glucose is soluble in water, but cyclohexane is not soluble in water. Well, that should be an easy answer. Why? Well, let's look at their long paragraph answer. Okay. The hydroxyl group. This is something you don't know what it is yet. This is an organic functional group, and all it is a hydroxide bonded to a carbon atom. That's all it is. Again, this is organic. You wouldn't know that. You're not required to know that. The hydroxide group and the glucose molecules can form strong hydrogen bonds with water. We should be able to recognize that at least it's going to get hydrogen bonds. So glucose is soluble in water. In contrast, cyclohexane is not capable of forming strong intermolecular attractions with water. Why? Then it goes into not as energetically favorable as interactions. Something crazy. But all that it boils down to is that right there. Water's polar, cyclohexane is non-polar. So glucose is polar and cyclohexane is non-polar. Polar solutes are generally soluble in polar. Non-polar are not. This right here, beautiful. This, no thanks. No thanks. To me, genuinely being honest, this is a ridiculous expectation. It really is. There's no way that you would ever get an 18 to 16-year-old student to write something this detailed oriented. It'd be impossible. I couldn't.
None of that comes to your, like, you
No.
don't think of those words.
No, and I agree. And so the expectations, the expectations they set forth. Now, bear in mind, this is a 2006 question. Times have changed a little bit, but point value, 1 point is earned for explaining the solubility of glucose in terms of hydrogen bonding with water. So basically you get the hydrogen bond. 1 point is earned for explaining the difference in polarity. So if you talk about how that the polar glucose can have a hydrogen bond with water and the nonpolar cyclohexane cannot because it's nonpolar, then you pretty much covered all your bases right there. All right, so looking at the next one. Consider the process represented below. Now notice, anytime you have a reaction that has multiple steps, what is this thing called? A mechanism. Very good. Notice what's happening here. We have water going from a what to a what? A liquid to gas. So is that a chemical or a physical change? Liquid to a gas. That's basically you're taking two water molecules and you're separating them. Is it still water? Yes. This is a physical change. Okay? That is something that so many students mess up every single year. Okay? You've got to look at it. Is it the exact same compound? It's the exact same thing. So it can't be physical. Excuse me, it can't be chemical. Now this time, water liquid is going to hydrogen and oxygen. You're taking that water molecule and essentially just knocking the crap out of it and splitting it in half. So this is a chemical change. And then let's look at this right here. First and foremost, positive delta H tells me it's what? Endothermic. Very good. So energy has to go how? Into the system. Spontaneous, non-spontaneous? Non. Very good. Which one of these obviously requires more energy? The bottom one, because it has more energy. All right. For each of the two processes, identify the types of, notice how it's worded, intermolecular or intramolecular. What is the difference there? Inter is between molecules. Intra is within the molecule. So inter means between. Intra is within. All right. So water. It going from a liquid to a gas. Process one is a physical change. What are you separating? Intermolecular forces or intramolecular? You're separating two water. So you're separating two intermolecular forces. But specifically, what type of intermolecular force does water have with each other? It has a hydrogen bonding. So this is inter, and so it's just going to be HB. Okay? Now, the other one, you're physically taking that water molecule and separating into it its two components. So now you're separating an intramolecular force. What are your two, and basically what I'm saying here is it's its bond. You're separating its bond. The two bond types are covalent and ionic, right? But you have to be very specific. What type of covalent molecule is that? A polar covalent. Very good. So in step 2, you're separating a polar covalent intramolecular force. All right, so let's look and see how their key phrases it out. Do what? I'm sure it's something wild and crazy. All right. In process 1, hydrogen bonds in liquid water are overcome to produce distinct water molecules in the vapor phase. So, I mean, that's easy to understand. Hydrogen bonds separate, or a physical change to separate your water molecules. Okay, process 2, covalent bonds. Now, here's the part that I have a problem with. It's not just covalent. It's more specifically what? Polar covalent bonds that you're technically separating. Because here's the thing. If it was a non-polar covalent, it would actually be less than that. Okay? Because your charges have been created. So within water molecules must be broken to allow the atoms to recombine in molecular hydrogen. This was actually one of the, I think it was on the multiple choice part of the mock exam. It had, and I'm only going to draw like 3 of them just to kind of prove a point. You may or may not remember it. It was on the mock exam. It was a multiple choice. And it had like, we'll call this one A, we'll call this one B, and it had 2 or 3 other things. And it said, which of these is an intramolecular force? What would that be? Do you remember that one? Okay. A would be the intramolecular. And then it may have even been, which one of these is an hydrogen bond? Well, where's your hydrogen bond? It would be B. It's the connection between the hydrogen of one water molecule and the oxygen molecule, because it's an in between 2 molecules. That was one of your multiple choice questions. But I think it was more of which one of these is. It was either said an intramolecular force, an intermolecular force, or hydrogen bond specifically. I think it was asking for the hydrogen bond specifically, if my memory serves me correctly. Okay. All right, so that covers that question. Real simple, straight to the point. All right, the last part, indicate whether you agree or disagree with a statement in the box below. Support your answer with a short explanation. When water boils, okay, we need to know something real quick. When water boils, what is the state of matter it's going from and to? Liquid to a gas. Is that a physical or a chemical change? This is physical. So what are you breaking? IMFs or bonds? Bonds are within. Are you separating that water molecule? No. So physical means IMFs are broken. Okay. So just out of that one word, we've got this information and this content. When water boils, water molecules break apart to form hydrogen molecules and oxygen molecules. So what are they essentially saying that we're forming? Very good. H2 and O2. True or false? What they're saying is true or false. It's false. Why? What did we just say? We're going from a liquid to a gas. Bingo. That's the exact key. What? No IMFs. Is that what it says? That's not true. That is absolutely not true. I showed it to him. I disagree with this statement. Boiling is simply a process. Is simply process number 1, in which only IMFs are broken, which is exactly what I just said. There you go. There. Only IMFs, not bonds. Okay. Only your IMFs are broken, and water molecules stay intact. So essentially what we're saying here is your bonds, no bonds are broken. Does that make sense, though? Okay. Nobody can hear you, though. So technically, if this were the diagram and they said water was boiling, what would you be breaking? Which would be A or B? Very good. So we'd be breaking this thing. But what if they said but what if the statement, it did not say boil, but we put water through electrolysis. Now what would electrolysis do? It would separate the H from the O, which then would make the statement true, and you could talk about how bonds would be broken. Does that make sense? You with me? All right. So in that case, when you go back to this, then your A would be broken. Okay, your A would be broken. All right. Let's move on down to this one. Consider 4 reaction energy profile from below. Is this still part of that same question? Wow, okay. First and foremost, let's kind of identify something. All right, so if we draw kind of a line like this, did the energy go up or down? Down, so it's XO or endo. That's XO. So it has what kind of sign? Negative. All right, same thing here. What is it? XO, negative sign, right? Okay. What about this one? XO, the exact same thing. Negative sign, but what about the last one? That was endo, very good. And it's what sign? Positive. Which one of these is non-spontaneous? The last one's non-spontaneous. Imagine if you have a ball, it's going to be much harder to get it over that hill than the other ones, okay? Identify the two diagrams that could represent a catalyzed and uncatalyzed reaction pathway for the same reaction. I need to actually get out of this view so it doesn't... There we go. Well, whatever. Identify the two diagrams that can be a catalyzed and uncatalyzed reaction pathway for the same reaction. Indicate which of the two diagrams represents the catalyzed pathway for the reaction. What do we know about a catalyst?
It lowers activation.
It lowers the activation energy. So essentially what we're trying to find is which hill has been altered, correct? Does the initial and final change any at all? Does it? No. The initial and final do not change at all. So, if you will notice, and I'm just going to kind of make a point of about it. Let's see if I can do this nice and pretty. Probably can't, but we're going to try. Do those two graphs have the exact same initial starting energy? Do they also have the exact same ending energy? Oh, man. Well, you saw how it worked, okay? So, but bottom line is they started and ended with the same amount. But what do we know about a catalyst? It only affects what? Activation energy. And the activation energy is only how large this hill is. All right? So which one has the larger hill? The one on the right, number 2, which means it is either catalyzed or uncatalyzed. It is uncatalyzed. Very, very, very good. That's exactly right. So going back and looking at the key, let me just double check, make sure. Diagram 1 represents a catalyzed pathway. Why? Because the activation energy hill is lower. And diagram 2 represents an uncatalyzed pathway for the same reaction. Why do you know, how can you tell they're the same reaction? The initial and the final are exactly the same.
So is that what a question like on today's exam?
Yeah.
They probably say, tell which one's catalyzed and uncatalyzed and explain.
And explain how you could tell. But justify. Because the initial and final energy values would be equivalent, and the catalyzed activation energy is less than the other one. That would be the perfect explanation for that. Very good. All right. All right. Indicate whether you agree or disagree with the statement of the box below. Support your answer with a short explanation. Adding a catalyst to a reaction mixture adds energy that causes the reaction to proceed more quickly. Why not?
Because a catalyst doesn't have energy, it lowers activation.
Fantastic. Fantastic. Very, very good. It does not add energy. It only allows the activation energy to be altered. That was one of the things that I found out at the mock exam that you guys probably did not get points for because of the way I explained stuff. I always said you add a catalyst. No, hang on. What was it?
Where you said it speeds up the reaction.
It speeds up, but there was something else that I didn't teach. Oh, it was explain how a reaction happens. And remember, it had sufficient energy and correct orientation. Here was the problem. Everybody got the sufficient energy and the correct orientation, but what I have failed to mention, and what the key said explicitly, is you had to mention it had sufficient energy to overcome the activation energy. And it said, bold and underlined, must mention activation energy. So everybody got both ideas, but it was that one little phrase that cost points. So again, adding a catalyst adds energy. That's the part that messes it up. It does cause the reaction to proceed more quickly. However, it provides an alternate pathway by lowering the activation energy. That's the key to that phrase. Is that the last question for that one? All right, awesome. So let's cancel that one. Get rid of this one. And all right, what question is this? 2006-7? Oh, man, I didn't need to close that one. 2006, Form A. Here we go. Yeah, but it's basically it's all these questions in one. Why is it bringing this up?
No, click on the sample questions.
Right here? Yeah, that's the answer, though. I don't want the answer. There we go. This is it. here we go. Now, I don't really want to spend...
This one is fast.
It should go fast. It says draw the complete Lewis structure for the SF3 cation in that. Well, what I'm going to do is let me just go ahead and show it to you and show you how we could have figured it out. First and foremost, the big thing, as soon as you see this, what do you have to do? The brackets and the... Now, I personally don't like the way that thing is drawn. I wouldn't draw it like that.
It confuses me
With the dots in the center? Yeah, I wouldn't draw it like that. Me personally, mine would look like this. It'd be SF, or it'd have this. It would have the lines. And you could have the dots around it. But how could you have known to do that? That's the kind of thing I want to focus on. How many S's do you have? There's one. I hate writing S's on this thing. There's one. There are 3 F's. And then you count up what? It's the valence electrons. S is in group 16, so it's got 6. Fluorine is in group 17, so it's got 7. So we have 6 plus 21. What is 21 plus 6? All right. As soon as you see that, something should throw a red flag up to you. It has to be an even number. You can never have one electron. So how do you correct for that? A plus. What do you do? Do you? What does a positive charge mean? You have lost or gained an electron. You've lost an electron, so you subtract. That is what everybody messes up. Everybody says, oh, well, it's positive, so you add an electron. And what you're going to do is you're going to end up having 2 extra pairs around the S, which is wrong. So you subtract 1. Why did I write 6? You subtract 1, which gives you 26. All right, well, if you count your bonds, 2, 4, 6, that gets you down to 20. And then you go the electrons around fluorine, which gives you 18. And so 18 minus, or 20 minus 18 leaves you 2. And anything you have left over, where does it go? On the center one, okay? Which will give you this structure. Now, the next part, identify the types of hybridization. How could you have known this? What do you count? Count everything attached to the central molecule. Do you include the extra pair? Yes. Okay. So how I kind of set it up is there's always 1 S, there are always 3 P's, and how many D's? 5 D's. Now, and this is, I've told you this, but they will not ever ask about D on the exam anymore. Okay. All right. So this is going to take care of our S, right? This is going to be one of our P's. This is going to be another one of our P's. And then you count that extra pair of electrons because it takes up space. So we have to count the areas. It's called a domain that occupies space around the central molecule. So it's 1, 2, 3, 4. So 1, 2, 3, 4. So it's sp3. No, just the areas around it. Okay? Just based off what you see, shape. Imagine, take this and then remove the top one. Trigonal, pyramidal. Very good. Trigonal pyramidal is shape. I don't even know if it's even asked that. I know that is correct. I didn't know if that's one of the questions it asked. All right. Identify the geometry that is consistent. Trigonal pyramidal or pyramidal, however you want to say it. Trigonal pyramidal. You hear some people say. All right. Predict whether the FSF bond angle and that cation is larger than, equal to, or smaller than 109.5. This is 107. So that automatically tells you what? It's smaller. But why is it physically smaller? All right. So what happens is this right here, imagine this being like a balloon. Okay, we got a balloon there. We got a balloon there. We got a balloon there, right? Those extra pairs of electrons actually take up more physical space than the bonds. All right? So since it takes up more space, what is it going to do to those three molecules? They're going to force them down at a further angle. So it gets them closer and closer and closer. So that's why your extra pair electron domain takes up more space. Therefore, it's going to squeeze those F's together. So again, if you want to read this, bond angle is expected to be slightly smaller than 109.5 because the repulsion between the non-bonding pair of electrons. Read that one more time. The non-bonding pair is the extra pair. Does that make sense? Okay. Non-bonding means it's not in a line. And the SF bonding pairs of electrons squeezes those two bond angles slightly together is all that it's asking for. Okay? All right. Now, it wants you to draw the SF5 anion. The first thing that we need to talk about is when you see this, what do you have to get going? Brackets and the charge. Now, it's negatively charged, so what do you do with your number this time? Add an electron. Very good. So since it's negative, we have to add that electron. Now, I don't like the way this structure is drawn at all, so let's kind of fix it how we would draw it more or less. All right, so S, there's only one of them, and we know that's going to be times 6, which gives us 6. We know F, there's 5 of them, times 7, which is 35. 35 plus 6 is 41. And how many do we add? Plus 1. So we have 42 total electrons. All right, so I'm going to stick S in the center. And then the way I would kind of recommend doing it is just making a pentagon. Does that make sense? Okay. And then from there, just add your F's. All right. And so that's 2, 4, 6, 8, 10. So 42 minus 10 gets us down to 32. And then every F gets its octet. So 2, 4, it's octet. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. So now we have 2 left, and where do we put them? And it's really hard to see in this particular diagram where those extra pair are, isn't it? Can you see where they are? That's your extra pair, which makes it really hard to see. So let me give you a hint. The way I would have drawn this, and this is how you see it sometimes, is it's like this. It kind of has a person with some eyes. Am I missing an F? All right. Well, that's not the right shape then. Let's try this. 1, 2. Is it 5 F's? 3, 4, 5. Yeah. So again, so essentially, if you want to say it's half a sun. Now, there is something that should kind of throw a red flag up to you. What's that red flag? Remember, every element should have at least how many? 8. Look at that sulfur. 2, 4, 6, 8, 10, 12. It's an expanded octet. Very good. So it has the ability to have a larger thing. Now, it may not even ask this, but I still want to do it anyways. Hybridization. Okay. So remember, there's 1 S. How many P's? 3. How many D's? All right, remember, you count everything bonded to the central, including the extra pair. So that takes care of your S. P1, P2, P3, then what? D1, and then D2. So SP3D2. That is your hybridization. But again, they won't ask you this question anymore on the exam because they no longer do dehybridizations. Me personally, give me as much as you can give me this stuff. It's easy. I love doing hybridization. If you know what you're doing, because my first year I looked and said, next. It's once I got taught how to count it, never had a problem ever since then. All right. So then identify the type of hybridization, again, based on the structure sp3d2. This is something you won't see, this square pyramidal. It's kind of funky. Don't worry about it. You won't see one like that. And then identify the oxidation number of sulfur in that compound. Okay, what? How do we figure that out? Oh, it'd help if I would write the formula, right? Come on. C S F 5. All right, you got the first part right. Set it equal to what? Y0. It's neutral. All right. All metals have the oxidation state of their group number. What group number is CS in? So it's a +1. What is the oxidation or charge of fluorine always? Why is it always -1? It is, but it's the most electronegative, so it always keeps its charge. Okay? So then, you just carry your math down. So we have -5. You have +1. So what's the only number that goes right there that it can be? Got to be a +4. You just cheer for questions like this, because I think it personally relatively simple. And that's it, guys. We're done. Nice, simple, smooth, easy questions.